This video reviews how capacitors work and also describes how capacitors can be combined with other capacitors or resistors in circuits. Recall that a capacitor is a device which stores charge and energy. When a capacitor is connected across the terminals of a battery, the plate that's connected to the positive terminal becomes positively charged, and the plate connected to the negative terminal gains a negative charge that is exactly equal in magnitude to the charge on the positive plate. The magnitude of the charge on each plate depends on the voltage of the battery and C, which stands for the capacitance of a given capacitor. The capacitance value is determined by the actual properties of the capacitor. The equation for capacitance is epsilon naught times A over A is the area of the two parallel plates, D is the distance between the two plates, and epsilon naught is the permittivity of free space. The permittivity of free space describes the space between the plates. We will assume that this space is a vacuum or free space. However, this can be filled with an insulating or conductorial, and this would change the capacitance and thus the charge. But we won't go there. We will assume that the space between the two plates is considered a vacuum. In addition to becoming charged, the capacitor also begins storing energy because as the charge moves onto the plates, more and more work is required to get the charges to move toward the other like charges because the electric force causes the two charges to repel. To determine the amount of energy stored, we use the equation 1/2 Q times V, where Q is the total charge, and we will use 1/2 the final voltage because we're choosing to use the average voltage. Here, the actual voltage varies as more and more work is done. C times V can be inserted for Q, because Q equals C times V for a capacitor, and we end up with the equation 1/2 CV squared for the energy stored in a capacitor. Multiple capacitors can be used in a given circuit, and just like resistors, we can wire them in parallel or in series. We will begin with parallel capacitors. Note that because each plate makes its own independent connection to both the positive and negative terminals of the battery, the final voltage across each capacitor will be equal to the voltage across the battery. As soon as a complete circuit is constructed, current and charge begin to flow. Note that because there are several paths for the charge to flow, the current or the charge splits up into each of the 3 different paths. So the total charge that leaves the battery, Q total, is equal to Q1 plus Q2 plus Q3, or the sum of the charges across each of the capacitors. Substituting the formula Q equals CV, we will come up with a formula for total charge, which is CEQ, or the equivalent capacitance, times the voltage equals C1 times V plus C2 times V plus C3 times V. Because the voltage is constant, we can cross it out of the equation, and we find the new equation for equivalent capacitance, or total capacitance, in parallel, which is CEQ equals C1 plus C2 plus C3, the sum of the individual capacitances. So adding capacitors in series, in parallel, increases the total capacitance because essentially the overall area on which charge can accumulate increases. we could actually replace the 3 capacitors with one single capacitor that has a surface area equal to the sum of the area of the individual capacitors, and this circuit would function exactly the same. Capacitors wired in series behave differently. Because there is only one path, the same amount of current must go through each capacitor. Positive charge leaves the positive terminal of the battery and heads toward the left plate of capacitor 1. Negative charge leaves the negative terminal of the battery and accumulates on the right plate of C3. In the area between capacitor 1 and capacitor 2, the negative charge in that conducting material moves to the left onto the right plate of capacitor 1 because it's attracted to the positive plate of capacitor 1. The positive charge in that area between C1 and C2 moves to the right onto the left plate of C2. And then, in the space between C2 and C3, like repel and unlike attract, so the negative charge moves to the left onto the right plate of C2, and the positive moves to the right onto the left plate of C3. The charge on each capacitor has the same magnitude charge. Also, due to conservation of energy, the total voltage of the battery is equal to the sum of the voltages across each capacitor, or V total is equal to V1 plus V2 plus V3. But the capacitor equation can be rearranged to solve for voltage, where V equals Q over C. Plugging in Q over C for V, we have the equation Q over C equivalent equals Q over C1 plus Q over C2 plus Q over C3. The charge on each of the plates is the same magnitude, so it cancels out of the equation, and we are left with the equation for the equivalent capacitance, or rather 1 over the equivalent capacitance. And from this equation, we can see that adding more capacitors in series actually makes the total capacitance decrease. And as a result, the equivalent or total capacitance is smaller than the smallest contributing capacitor. From these relationships, we can see that the forms of the equations for capacitors in series and parallel are reverse that of resistors in series and parallel. Recall, our equation for resistors in series is equal to the sum of the individual resistances. But for capacitors in series, the formula looks a little bit different. And then, again, recall the equation for resistors in parallel. And we see that the capacitors formula in parallel is different. Just as we combine series and parallel resistors in combination circuits, we can combine series and parallel capacitors. Let's try an example. In this example, capacitor 1 is in series with capacitor 2 and capacitor 3, which are parallel to each other. The question is, determine the charge on each capacitor and the voltage across each if the capacitance is the same for each at 3 microfarads, and the battery voltage is 4 volts. Pause the video to review the problem. So here's our solution.